So let's start by doing some problems using the properties of light and the photoelectric effect. So a photon of green light has a wavelength of 520 nanometers. We want to find the photon's frequency, momentum, and energy. So what's the frequency? Frequency, remember we have the equation C equals F lambda. So we're just going to do the same thing that we did in a couple of chapters ago and do F is equal to C over lambda. So C is the speed of light, 3 times 10 to the 8 meters per second. The wavelength is 520 nanometers, so I need to write that 520 nanometers into meters. So 520 times 10 to the minus 9 meters. And I get 5.77 times 10 to the 14 hertz. Okay, so there's the frequency. Next thing is the momentum. And we had two equations for the momentum. Let me write them over at the side. We had momentum is H equal to HF over C, or momentum is equal to H over lambda. Those are equivalent equations. So I could use either of those now I found the frequency, but usually I like to try to do my calculations with things I'm actually given in the problem, and then if I messed up on my calculation of the frequency, I won't get the momentum wrong. All right, so momentum is equal to H. H is Planck's constant. That's 6.626 times 10 to the minus 34 in units of joule seconds. So I do that divided by the wavelength, 520 times 10 to the minus 9 meters, and I get 1.274 times 10 to the minus 27. I guess I should take that down to 2 sig figs, so 1.3 times 10 to the minus 27. And if you remember from Physics 1, momentum is mass times velocity, so the units are kilograms for mass and meters per second for velocity. Okay, last part, find the energy. So the energy is equal to HF of a photon. So H, again, Planck's constant, 6.626 times 10 to the minus 34 joule seconds. The frequency, 5.77 times 10 to the 14 hertz. Okay, so remember hertz is 1 over second. So that means my seconds are going to cancel. I'm going to be left with energy in joules. So I'm going to get 3.82 times 10 to the minus 19 joules. Okay, sometimes you're asked to find the energy in electron volts. Okay, so if I were asked to find the energy in electron volts, there's two ways I could do it. One way is I could do it this way, and then I could convert the joules to electron volts. So remember, I want to get rid of the joules, go to EV, so I'll write my fraction that way. 1 EV is 1.6 times 10 to the minus 19 joules, and so I get 2.39 EV. Another way to do the problem is if you're asked initially to find the energy in EV, we can use Planck's constant in terms of units of EV seconds, which is 4.136 times 10 to the minus 15 EV seconds. And I could just have done the calculation that way, and I would have got the same answer, 2.39 electron volts. So you can do it either way. Okay, so now let's do a photoelectric effect problem. So in a photoelectric effect, we have light that falls on a surface and it kicks off electrons, and we know that our equation is that the maximum kinetic energy of the electrons that come out is equal to the energy of the light coming on minus the work function for the surface, which is the amount of energy, minimum amount of energy that it takes to pull an electron out of the surface. So we're told in this problem that the light has a wavelength of 400 nanometers. So 400 nanometers, 400 times 10 to the minus 9 meters. And the maximum kinetic energy is 1.1 eV. oops, Ke max equals 1.1 EV. And I want to find the work function. So I want to rearrange that red equation to give me the work function. So if I rearrange, I get the work function is equal to HF minus Ke max. So to do this, I'm going to have to find the frequency. To get the frequency, I'll do the same thing that I did in question 1. So frequency is C over lambda. So 3 times 10 to the 8 for C, 400 times 10 to the minus 9 for my lambda, and I get 7.5 times 10 to the 14 hertz. Okay, so now I can plug my frequency into this equation. So I got work function is equal to HF minus Ke max. Now my Ke max is in electron volts. So there's 2 ways I could do this. Remember, I've got my 2 values for Planck's constant, 6.626 times 10 to the minus 34 joule seconds. Or I've got H is equal to 4.136 times 10 to the minus 15 EV seconds. So I can do this calculation with it with the Planck's constant in joules, and then I'm going to have to convert my Ke max into joules to do it. So if I do that, remember, write it beside it. So I'm going to do my conversion. Now I want to get rid of the EV and go to joules. So 1 EV is 1.6 times 10 to the minus 19 joules. So my Ke max is 1.76 times 10 to the minus 19 joules. Okay, so my work function in that case, so I would do 6.626 times 10 to the minus 34 joule seconds. I'm going to write the units there so we remember what we're going to get our answer in. Times F, 7.5 times 10 to the plus 14 hertz. And then I'm going to subtract my Ke max, 1.76 times 10 to the minus 19 joules. So I got the same units, joules and joules. And I get 3.21 times 10 to the minus 19 joules. Okay, or equivalently, I could have done it, let me do it, I'll do it in red. In EVs, 4.136 times 10 to the minus 15 joule seconds times 7.5 times 10 to the 14 minus 1.1 EV. So now, oops, that's not joule seconds over here, that's EV seconds, sorry. So now I've got my units in EVs, and I get 2.0 electron volts. Okay, so there's 2 ways I could do the problem, depending on how I want to get my answer out. So if I want my answer for the work function in electron volts, then it's easier just to do it this way in the red, so that I don't end up having to convert Ke max. Okay, the other way to do it would be to do it in joules, and then I can convert my 3.2 times 10 to the minus 19 joules, do the conversion into EV. Okay, so 1.6 times 10 to the minus 19 joules and 1 EV, and I would still get 2.0 EV. So whichever way makes you more comfortable. The way I did it in red, you didn't have to do any conversions. The way you did it in black, you had to do 2 conversions. First, you had to convert the Ke max into joules, and then you had to convert your final answer back into EV. All right, so that's part A. Part B says, what's the maximum kinetic energy that you'll get if the incident light is changed to a 300 nanometer wavelength? All right, so now lambda is equal to 300 nanometers. So our frequency, C over lambda, 3 times 10 to the 8 over 3 times 10 to the minus 7, or 300 times 10 to the minus 9, however you want to write it. I get 1 times 10 to the 15 hertz, so I get a bigger frequency, and so I've got a bigger energy, and so I'd expect that I'd have a bigger energy of electrons getting kicked off, because if I have more energy of light coming in, then the electron should be bounced off with more energy. All right, so let's figure this out. And again, I can do this two ways. So now I know my work function both in EV and in joules. So let's do it in joules first. So I got HF, 6.626 times 10 to the minus 34. I'm going to use my joules unit for EV times my frequency, 1 times 10 to the 15 hertz, minus the work function in joules. So I have to keep my units the same. And I get 3.42 times 10 to the minus 19 joules. Or I could have done it all in EV. So let me go to red just to signal what I'm doing here. All right, so now I'm going to use my Planck's constant in EV. Okay. Frequency minus my work function in EV, which was 2.0, and I get 2.13 EV. And again, I could have taken my joules and converted it. So I could do, let's see, I want to get rid of the joules, go to EV. So I'm going to do 1.6 times 10 to the minus 19 goes with the joules, 1 with this, and I would still get 2.13 EV. Or equivalently, I could have converted my number in red back to joules. Okay, so you've got a bunch of different options, right? So if your problem asks for the answer in joules, or if it asks for it in EV, just do whichever way you feel most comfortable doing it.